This module introduces MapReduce and Hadoop and contains the following topics. Topic 1. Hadoop Architecture. Topic 2. MapReduce Framework. Topic 3. MapReduce Programming. Topic 4. MapReduce and HDFS S3. Topic 5. Use Case Recommendation Engine. You will be able to understand Hadoop architecture, understand the MapReduce programming framework, including the map, shuffle and sort, and reduce components. Understand MapReduce APIs. Understand how these technologies can be applied to solve a business use case. What is Hadoop? Hadoop is a programming framework that supports the processing of large data sets in a distributed computing environment. Hadoop makes it possible to run applications on systems with thousands of nodes involving thousands of terabytes. Its distributed file system facilitates rapid data transfer rates among nodes and allows the system to continue operating uninterrupted in case of a node failure. This approach lowers the risk of catastrophic system failure, even if a significant number of nodes become inoperative. What is Hadoop designed for? Hadoop is designed for offline processing of large-scale data. Hadoop is best used as write once and read many type of data store. Hadoop is not designed for random reading and writing a small number of records. It is not meant for online transaction processing or OLTP applications. Hadoop architecture is comprised of two basic units, the data processing unit and the data storage unit. MapReduce is a parallel processing framework that is massively scalable. It has been designed to work in tandem with the Hadoop Distributed File System, or HDFS. In traditional systems, computation is performed after data is moved from the storage location to the compute location. This is dependent on network bandwidth, which is a bottleneck as large amounts of data are moved. With Hadoop and MapReduce, computation is executed at the location of the data, alleviating many issues experienced in traditional systems. Click the buttons to learn more. The data processing unit consists of task trackers and job trackers. The task tracker resides in each data nodes, and the job tracker resides in the name node. The job tracker is the controller for the entire job and assigns tasks to each task tracker in the data nodes. HDFS is the data storage unit and consists of the following components. Name node. This is the primary node which holds control and configuration information. It acts as the single point of contact for the client. Client applications talk to the name node whenever they want to locate a file or when they want to add, copy, move, or delete a file. Data node. This is where the data is stored. Secondary name node. This is a helper node for the name node performing key support activities. Hadoop data storage is taken care of by HDFS. HDFS has a master and slave node architecture. HDFS clusters consist of a single name node, secondary name node, and multiple data nodes. HDFS stores each file as a sequence of blocks. All blocks in a file has same size except the last block. The blocks of a file are replicated for fault tolerance. The block size and replication factor are configurable. Click the buttons to learn more. The name node is the master of the system. It maintains the name system of directories and files and manages the blocks that are present on the data nodes by maintaining metadata for the files that are stored in a cluster. Without the metadata on the name node, there is no way to access files in the HDFS cluster. Data nodes are slaves in Hadoop where the actual data is stored. They are responsible for serving read and write requests from the file system's clients. Data nodes also perform block creation, deletion, and replication upon instruction from the name node. The name node is the master of the system. It maintains the name system of directories and files and manages the blocks that are present on the data nodes by maintaining metadata for the files that are stored in a cluster. Without the metadata on the name node, there is no way to access files in the HDFS cluster. The secondary name node is a helper node for name node. It is commonly misunderstood as a substitute for the name node, but it is not a substitute for the name node. It communicates with the name node to take snapshots of HDFS metadata at regular configurable intervals to create checkpoints. In the event of name node failure, you can restart the name node by using the checkpoint as reference, which minimizes downtime data loss. The secondary name node is typically run on a different computer than the primary name node. Memory requirements are similar to those of the primary name node. MapReduce is a software framework for performing distributed data processing using parallel and distributed algorithms on large clusters. Click the buttons to learn more. As we learned earlier, MapReduce has two major components. The job tracker is the master of the system and manages jobs and resources via task trackers in the cluster. The job tracker schedules each map action as close as possible to the actual data being processed. For example, on the task tracker, which is running on the same data node as the underlying block. Task trackers are the slaves which are deployed on each machine. They are responsible for running the map and reduce tasks as instructed by the job tracker. This framework has two task processing steps or phases known as the map and reduce phases, which we will learn more about later in this module. Let's try to gain a deeper understanding of the Hadoop architecture by looking at a job flow as a sequence of steps where each component plays its role. First, input data to be processed is copied to the distributed file system or DFS. DFS makes a remote procedure call or RPC to the name node to create a new file in the file system's namespace. After performing various checks, if the name node finds that the request is valid, It makes a record of the new file. It splits the data into blocks and writes these data blocks to the data nodes. The next step is the starting point of the Hadoop job, where the user submits a job to the client. The client gets input file information, including location and names. At this point, the client also splits big jobs into multiple smaller jobs. Job information is then uploaded into DFS. The client then submits the job to the job tracker. The job tracker initializes the job and sends it to a job queue. The job tracker reads the job files from DFS and begins creating maps and reduces. Each data node continuously sends heartbeat information to the name node to let the name node know it is alive and running. The job tracker then picks the job from the queue. The job tracker then finally assigns the task to the task tracker to process the data in the data node. Each task or computation occurs in the slave nodes. Hadoop 2.x was recently released. New features of Hadoop 2 include the following: HDFS snapshots, which are useful during failover. The ability to use the NFS v3 file system to access data in HDFS. NFS v3 is used to access files over a network much like local storage is accessed. Support for running Hadoop on Windows. Binary compatibility for MapReduce applications built on Hadoop 1.0, mainly for reusability purposes. A substantial amount of integration testing with other components in the Hadoop ecosystem, such as Pig and Hive. Yet another resource negotiator, or YARN, is a re-architecture of Hadoop that allows multiple applications to run on the same platform. With YARN, applications run in Hadoop instead of on Hadoop. YARN was designed to address issues with MapReduce 1, including scalability issues. MapReduce 1 has a limitation of approximately 4,000 machines. Inflexible resource management. Inflexible slot configuration on nodes, which can lead to underutilization of resources. Click the buttons to learn more. In Hadoop 1, a single name node managed the entire namespace for a Hadoop cluster. In Hadoop 2, with the introduction of HDFS federation, multiple name node servers manage namespaces. This allows for horizontal scaling, performance improvements, and multiple namespaces. The implementation of HDFS federation allows existing name node configurations to run without changes. Prior to Hadoop 2.0, name node was a single point of failure in an HDFS cluster. Each cluster had a single name node. If that machine or process became unavailable, the cluster as a whole would be unavailable until the name node was either restarted or brought up on a different machine. The HDFS high availability feature in Hadoop 2.0 and later versions provides the option to run two redundant name nodes in the same cluster in an active-passive configuration with a hot standby. This allows a fast failover to a new name node in case a machine crashes, or if a failover is initiated by an administrator as part of planned maintenance. Processing control. Hadoop 1 uses the job tracker and task tracker to control job execution and job flow. However, the inflexible slot-based memory management model can cause either underutilization or overutilization of resources, which can negatively affect performance. In Hadoop 2, the job tracker and task tracker have been replaced by three components. The resource manager, which is a scheduler that allocates available resources in the cluster to competing applications. The node manager, which runs on each node in the cluster and takes direction from the resource manager. It is responsible for managing resources available on a single node. And the application master, which runs a specific YARN job and is responsible for negotiating resources from the resource manager and works with the node manager to execute and monitor containers. AWS provides a one-stop solution to develop and run your Hadoop applications. Open source projects that run on top of the Hadoop architecture can also be run on Amazon EMR. The most popular applications, such as Hive, Pig, HBase, and Ganglia, are already integrated with Amazon EMR. Amazon EMR is a managed Hadoop service that makes it easy to install Hadoop ecosystem applications, configure and manage your Hadoop cluster, and run your cluster on EC2 instances. You can use Amazon S3 for storage with Amazon EMR as well. You can also manually install Hadoop on Amazon EC2 instances. Click the button to learn more. Amazon EMR is the most performant, reliable, secure, easy, and cost-effective way to run Hadoop on AWS. With Amazon EMR, you can easily provision one, hundreds, or thousands of Amazon EC2 instances in your Amazon EMR cluster to process data at any scale. Additionally, Amazon EMR has tight integration with Amazon S3 for durable and low-cost object storage, and can also output logs to S3 for easy access. Integration with the Amazon EC2 spot market to save money when resizing your cluster, and automatic cluster management. Customers launch millions of Amazon EMR clusters every year. Visit http://aws.amazon.com/elasticmapreduce/ for more information.